In 1935, Albert Einstein tried to prove that quantum mechanics was broken. He failed, but in failing, he accidentally described the strangest phenomenon ever discovered in physics, something so unsettling he refused to believe it was real, even as the evidence piled up against him. Einstein was not a man who doubted his own instincts lightly. He had already rewritten the laws of space and time. He had already shown that gravity itself was a curve in the fabric of the universe. He was not someone easily rattled by strange ideas. But quantum mechanics rattled him. Not because it was wrong exactly, but because it seemed to describe a universe that did not behave the way any universe should. A universe where particles did not have definite properties until someone looked at them. A universe where two objects, separated by any distance you like, could somehow be connected in a way that defied everything he understood about how information and influence move through space. So in 1935, working with two younger physicists, Boris Podolsky and Nathan Rosen, Einstein set out to expose what he saw as a fatal flaw in quantum theory. Their paper became known by the initials of its authors, EPR. The argument was elegant and on the surface devastating. Imagine two particles that interact briefly and then fly apart, moving in opposite directions, out toward opposite ends of the universe, if you like. Quantum mechanics predicts that these two particles remain linked. Measure a property of one, and you instantly know the corresponding property of the other, no matter how far apart they have traveled. Einstein looked at this prediction and said, "That cannot be real physics. That would require some kind of influence traveling faster than light," which his own theory of relativity forbade. He called it spooky action at a distance, and he meant it as an insult. He believed the only sane explanation was that the particles must have secretly carried hidden information with them all along, information quantum mechanics simply failed to describe. The theory, he argued, was incomplete. Reality had to be more orderly than quantum mechanics allowed. There had to be hidden variables, some deeper layer of physics that would restore common sense to the universe. For decades, nobody could test who was right. The tools did not exist. The mathematics needed to distinguish Einstein's hidden variables from the genuine weirdness of quantum theory had not even been invented yet. Einstein died in 1955, still convinced that the universe could not be as strange as quantum mechanics insisted. He never got to see how the story ended, and the ending, when it finally came, proved him wrong in one of the most stunning experimental verdicts in the history of science. To understand what entanglement actually is, you have to let go of an assumption that feels almost too obvious to question. The assumption that every object has its own separate, independent identity. In classical physics, this is simply true. A rock sitting on a table has a location, a mass, a temperature. Those properties belong to the rock. They do not depend on some other rock 1,000 miles away. But in quantum mechanics, this assumption can break down completely. When two particles become entangled, their properties are no longer separately defined. You cannot describe particle 1 on its own, and you cannot describe particle 2 on its own. The only complete description that exists is a description of the pair, together, as a single unified system. It is a bit like trying to describe a single dance step performed by one half of a dancing couple. The step only makes sense in relation to the partner. Separate them in your description, and the meaning falls apart. This is not a matter of us simply not knowing the individual properties yet, the way you don't know the outcome of a coin flip until you look, where the coin has already landed on heads or tails, and you simply have not lifted your hand to check. That analogy, tempting as it is, turns out to be exactly the wrong way to think about entanglement. And understanding why is the whole key to grasping what makes this phenomenon so different from anything in classical experience. It is something deeper. According to quantum theory, the individual properties genuinely do not exist in a definite state until a measurement is made. Before you measure, the particle exists in what physicists call a superposition, a kind of blended state holding multiple possibilities at once. It is only the act of measurement that forces one specific outcome to appear. And here's the strange part that so upset Einstein. When two particles are entangled, the moment you measure one and force it into a definite state, the other particle's state becomes definite too, instantly, even if it is on the opposite side of the galaxy. Spin one up, and its entangled partner is spin down, every single time. Not most of the time, not usually. Every time, with perfect correlation, as though the two particles were still somehow whispering to each other across an impossible distance. Einstein's hidden variable idea offered a comforting alternative. Maybe the particles were never truly undefined. Maybe they left their point of origin already carrying a secret, predetermined answer, like two sealed envelopes mailed to opposite ends of the world, each already containing the same hidden instructions. Open one envelope, and of course you learn what is written in the other, because the answer was fixed all along. No mystery, no spooky action, no problem for relativity. It was a completely reasonable idea. The only trouble was, nobody could figure out how to test it. Until 1964, when an Irish physicist named John Stuart Bell changed everything. Bell did something remarkable. He did not try to guess whether Einstein or the quantum physicists were right. Instead, he found a way to turn philosophy into mathematics. He proved that if Einstein were correct, if hidden variables truly determined the particle's properties in advance, then the statistical correlations between measurements on entangled particles would have to obey a certain mathematical limit. This limit became known as Bell's inequality. It set a ceiling. No hidden variable theory, no matter how clever, could produce correlations stronger than that ceiling allowed. But quantum mechanics made a very different prediction. It predicted that entangled particles would violate that ceiling, producing correlations stronger than any hidden variable theory could ever explain. For the first time, there was a real experiment that could be run, a test with a genuine, falsifiable answer. Either nature would respect Einstein's ceiling, proving hidden variables were real, or nature would break straight through it, proving that quantum entanglement really was as strange as the equations suggested. It took almost 2 decades for the technology to catch up with Bell's idea. In the early 1980s, a French physicist named Alain Aspect built one of the first experiments precise enough to actually test the inequality with entangled photons, particles of light. He and his team generated pairs of entangled photons, sent them flying off in opposite directions, and measured their polarization using detectors set at carefully chosen angles. The results were unmistakable. The correlations broke Bell's inequality. They broke it decisively, matching the predictions of quantum mechanics almost perfectly. Nature had made its choice, and it had not chosen Einstein's tidy, orderly universe of hidden variables. It had chosen the spooky one. Of course, science is rarely satisfied with a single decisive result. Skeptics pointed to gaps in these early experiments, called loopholes, subtle ways that hidden variables might still sneak through undetected. Maybe the detectors were not truly independent. Maybe some faster-than-light signal was somehow being smuggled between the measurement stations without anyone realizing it. Over the following decades, physicists closed these loopholes one by one, with increasingly elaborate and clever experimental designs. They used random number generators tied to distant astronomical events to choose measurement settings, so that no earthly signal could possibly have coordinated the outcome in advance. They separated detectors by greater and greater distances. They achieved near-perfect detection efficiency, ruling out the possibility that some hidden bias in undetected particles was skewing the results. One especially clever experiment used light from distant quasars, galactic beacons whose light had been traveling toward Earth for billions of years, to randomly determine the measurement settings on each side. The reasoning was almost poetic. If some conspiracy of hidden variables was somehow rigging the results, it would have had to begin arranging that conspiracy billions of years ago, before life on Earth even existed, before the planet itself had formed, which is about as close to ruling out coincidence as an experiment can get. Every single test, no matter how carefully designed to leave no escape route, produced the same verdict. Quantum entanglement was real. The correlations were genuinely stronger than anything a classical, hidden variable universe could produce. Einstein's spooky action at a distance was not a flaw in the theory. It was a fact about reality. In 2022, the Nobel Prize in Physics was awarded to 3 scientists for this exact body of work: John Clauser, Alain Aspect, and Anton Zeilinger. The prize committee recognized what had, by then, become one of the most thoroughly tested and confirmed phenomena in all of physics, a phenomenon that took nearly 90 years to travel from Einstein's skeptical thought experiment to an accepted foundational pillar of how we understand the universe. It is worth pausing on how remarkable that journey really is. A theoretical argument designed to disprove quantum mechanics ended up becoming one of its most celebrated confirmations. Einstein built the very tool that would eventually be used to prove him wrong. Now, here is where most explanations of entanglement go astray, and it is worth taking a moment to clear up the confusion properly, because it matters. When people hear that measuring one particle instantly affects its entangled partner, no matter the distance, the natural next thought is that this must allow some kind of faster-than-light communication. Science fiction loves this idea. Instant messages across galaxies, unhackable instantaneous contact between distant starships, that sort of thing. But it does not work that way, and understanding why is actually one of the most beautiful parts of the whole story. Here is the catch. When you measure your particle, you get a completely random result. You cannot control which outcome you get. You might get spin up, you might get spin down, and there is no way to choose. Your entangled partner on the other end, far away, also gets a result the instant their measurement happens. And it will always correlate perfectly with yours. But from their perspective, sitting alone with no other information, the result also looks completely random. They have no way of knowing, just from their own measurement, whether you have measured your particle yet at all. The correlation only becomes visible, only becomes meaningful, once the two observers compare their results through some ordinary classical channel of communication. A phone call, an email, a radio signal, something that cannot travel faster than light. Only then, comparing notes side by side, do they see the eerie pattern of perfect correlation emerge. So no information actually crosses the distance instantaneously. No message can be sent this way. What is transmitted instantly is a correlation, a pattern, but not a controllable signal. Nature, it turns out, is clever enough to be profoundly strange without breaking the speed limit that Einstein's own theory of relativity demands. The two great pillars of 20th century physics, relativity and quantum mechanics, managed to coexist without contradiction, even here, even in the strangest of corners. So if entanglement cannot send messages, what good is it? As it turns out, tremendous good. And this is where the story shifts from philosophy into engineering, from thought experiment into technology that is being built right now. Consider quantum computing. Ordinary computers process information using bits, tiny switches that are either off or on, representing a 0 or a 1. Quantum computers use qubits instead, and qubits can exist in superposition, holding a blend of 0 and 1 simultaneously. That alone gives quantum computers unusual power. But the real magic, the thing that separates a quantum computer from simply being a very strange classical computer, comes from entanglement. When qubits become entangled with one another, the computer can process an enormous, exponentially growing space of possibilities all at once, in a way that has no classical equivalent whatsoever. Certain problems that would take a classical supercomputer longer than the age of the universe to solve could, in principle, be solved by a sufficiently powerful quantum computer in a matter of hours or even minutes, breaking certain forms of encryption, simulating complex molecules for drug discovery, modeling chemical reactions atom by atom in ways no classical computer could ever hope to match, optimizing massive logistical systems with more variables than any brute force method could handle. Entanglement is the resource that makes all of this theoretically possible. Without it, a quantum computer is just an expensive, fragile version of an ordinary one. With it, you unlock computational power that genuinely has no classical analog. This is also why building a working quantum computer is so brutally difficult. Entangled qubits are extraordinarily delicate. The slightest disturbance from the outside world, a stray vibration, a fluctuation in temperature, a wandering electromagnetic field, can cause the entanglement to collapse, a process physicists call decoherence. When that happens, all the quantum advantage disappears, and the machine behaves like nothing more than a slow, unreliable classical computer. This is why today's leading quantum computers are cooled to temperatures colder than deep space, colder than the empty vacuum between galaxies, isolated inside vibration-dampened chambers and shielded from every stray signal engineers can think to block. Companies like Google, IBM, and a growing list of specialized quantum computing startups are locked in a race to preserve entanglement for longer, across more qubits with fewer errors, because whoever solves that engineering puzzle first will hold an enormous technological advantage. It is a strange twist of history that the very property Einstein found so implausible he refused to accept it has become the single most valuable resource in an entire emerging industry. Then there is quantum cryptography, and this application flips the strangeness of entanglement into something remarkably practical, secure communication. Imagine two people, traditionally named Alice and Bob in physics literature, who want to share a secret encryption key without anyone else intercepting it. If they use entangled particles to generate that key, something remarkable happens. Any attempt by an eavesdropper to intercept and measure the particles along the way inevitably disturbs the delicate quantum state. It leaves a detectable fingerprint. Alice and Bob can check for this disturbance, and if they find it, they know immediately that someone was listening, and they simply throw out that compromised key and try again. This is not encryption that relies on mathematical difficulty, the way most of today's internet security does, difficulty that could, in principle, eventually be cracked by a sufficiently powerful computer. This is encryption secured by the actual laws of physics themselves. Eavesdropping is not merely difficult. It is, in a fundamental sense, physically detectable every single time it happens. Several countries have already built and tested quantum key distribution networks using this exact principle, some running for hundreds of kilometers through fiber optic cable, some transmitted through satellites orbiting far above the atmosphere. There's also quantum teleportation, a name that sounds like science fiction but describes something real, if considerably less dramatic than the term suggests. Quantum teleportation does not move matter or energy from one place to another. What it does is transfer the exact quantum state of one particle onto a distant particle, using entanglement as the underlying resource, combined with a small amount of ordinary classical communication to complete the process. In effect, the information describing a particle's precise quantum condition can be reconstructed somewhere else entirely, while the original state is destroyed in the process. So nothing is duplicated, nothing violates the rules of physics. This has already been demonstrated across surprisingly long distances, including through satellite links stretching well over 1,000 kilometers, and it forms a crucial building block for how future quantum networks are expected to transmit and preserve fragile quantum information across long stretches of the globe. There is one more application worth pausing on, because it rarely gets the attention it deserves, even though it may end up being one of the most immediately useful, and that is quantum sensing. Entangled particles can be used to build measurement devices that are more precise than anything classical physics allows, because the correlations between entangled particles can be exploited to reduce the random noise that normally limits how finely you can measure something. Entangled atoms have been used to build clocks accurate enough that they would not lose a single second over the entire age of the universe. Clocks so precise that they can detect the subtle slowing of time caused by a difference in elevation of just a few centimeters, a direct consequence of Einstein's own theory of relativity, measured using the very quantum effect he doubted. Entangled photons are being used to develop imaging systems that can see through fog, through biological tissue, through scattering environments that would blind an ordinary camera, by exploiting correlations that classical light simply cannot produce. Gravitational wave detectors, the extraordinarily sensitive instruments that first detected ripples in space-time from colliding black holes, now use a technique called squeezed light, a close cousin of entanglement, to push their sensitivity beyond what was once considered a fundamental physical limit. In every one of these cases, the strangeness that so troubled Einstein is being converted, quite literally, into sharper eyes for humanity. Instruments that let us see and measure the universe with a precision that would have seemed like magic a century ago. Which brings us to what many physicists consider the next great frontier, something often called the quantum internet. The idea is to build a network where entanglement itself becomes the transport medium, connecting distant nodes, whether they are quantum computers, quantum sensors, or secure communication hubs, allowing any 2 points on this future network to share entangled particles on demand. This is not a distant fantasy. It is being actively built piece by piece in laboratories and test networks around the world right now. Researchers at NIST recently sent entangled photons across 62 kilometers of ordinary commercial optical fiber from their campus in Maryland to a nearby university, demonstrating that fragile entangled states can survive the noisy, imperfect conditions of a real-world fiber network, not just the pristine, isolated environment of a laboratory bench. Other teams have shown that entangled photon pairs can be produced using nothing more exotic than ordinary sunlight, a discovery that surprised many in the field, since generating entanglement had long been assumed to require the precise control of specialized lasers. Physicists have also recently entangled moving clouds of atoms for the first time, colliding them together and tracking the resulting correlated patterns as the particles scattered apart, opening entirely new territory for testing the deepest foundations of quantum theory, and even probing at tentative connections between entanglement and gravity itself. That last point deserves a moment of its own, because it leads into some of the most exciting and speculative territory in modern theoretical physics. A growing number of researchers now suspect that entanglement might not merely be a strange quirk that occurs within spacetime, but something that actually helps build spacetime in the first place. The idea, still very much a work in progress, still being debated and refined, suggests that the geometric fabric of space itself, the very distances and connections that define how far apart 2 points are, might emerge from networks of entangled quantum information. In other words, entanglement might not just be a phenomenon that happens inside the universe. It might be part of what stitches the universe together in the first place, the underlying thread from which the fabric of reality is woven. This remains a frontier of active research, not settled fact, but it represents one of the most ambitious ideas in physics today, an attempt to unify quantum mechanics and gravity, two theories that have famously refused to fit neatly together for the past century. Still, for all its strangeness, for all the philosophical vertigo it induces, entanglement is no longer just an abstract puzzle debated by theorists in university lecture halls. It has become an engineering challenge, one being tackled by companies and national laboratories, investing enormous resources into making these fragile quantum states practical, stable, and scalable. The central obstacle is not a gap in our understanding of the physics, which has been tested and confirmed again and again with extraordinary precision. The obstacle is engineering. Entangled states are notoriously fragile. They are easily disturbed by heat, by vibration, by stray electromagnetic noise, by nearly anything in their environment that jostles them even slightly. Preserving entanglement over long distances and long timescales, while still being able to use it for computation or communication, is an enormous technical undertaking. Fiber optic cables lose signal strength over distance, and without special devices called quantum repeaters, something researchers are still racing to perfect, entangled signals tend to fade out after roughly 100 kilometers. Satellite links offer one promising workaround, though they introduce their own challenges, precise pointing across vast distances, compensating for atmospheric turbulence, and timing everything with the orbits of moving spacecraft. None of these are fundamental barriers written into the laws of physics. They are simply hard, patient, expensive problems of engineering, the kind that tend to fall piece by piece to persistent human ingenuity over time. What makes this story so compelling is not just the strangeness of the physics, though that alone would be enough to capture anyone's imagination. It is the arc of the whole journey, a thought experiment designed to disprove a theory, a mathematical inequality that turned philosophy into something testable, decades of increasingly precise experiments that closed every possible loophole, a Nobel Prize that confirmed what Einstein himself refused to accept. And now, laboratories around the world racing to turn this once purely theoretical curiosity into working technology. Computers that could solve problems no classical machine ever could. Communication systems secured not by mathematical complexity, but by the fundamental laws of the universe itself, and a tentative, tantalizing hint that this strange correlation between particles might be woven into the very structure of space and time. Einstein looked at entanglement and saw something broken, a sign that quantum mechanics had to be incomplete. He was wrong about that. But he was right about something else, something perhaps even more important. He was right that this phenomenon deserved to be taken seriously, examined rigorously, and tested to its absolute limits rather than simply accepted on faith. That rigor, that refusal to accept spooky claims without proof, is exactly what eventually confirmed entanglement as real, undeniable, and fundamental. 90 years after Einstein first called it spooky, entangled particles are being sent through city-sized fiber networks, generated using nothing more than sunlight, and studied as a possible thread in the fabric of the cosmos itself. The universe, it turns out, is stranger and more deeply interconnected than Einstein ever wanted to believe, and we are only just beginning to learn what that interconnection might let us do. Perhaps the most humbling part of the whole story is what it says about the limits of human intuition. Our brains evolved to survive on the savannah, to track the motion of predators and the trajectory of thrown rocks, to reason about a world of objects with definite locations and definite properties. Nothing in that evolutionary inheritance prepared us to understand a universe where two particles can share a single unified state across any distance, where properties do not exist until they are observed, where reality itself seems to resist being pinned down until the moment someone looks. Entanglement forces us to admit that the universe was never obligated to make intuitive sense to a species of curious primates. It only had to be internally consistent and mathematically precise and endlessly, rigorously testable. On every one of those counts, entanglement has passed with a level of certainty that few ideas in the history of science can claim. So the next time someone tells you that quantum mechanics is too strange to be real, remember Einstein, the man who invented the very argument meant to expose that strangeness as a flaw, and who ended up, instead, handing the world one of its greatest and most useful discoveries.